Hello. As promised last time, the promise I failed to deliver on, I'm going to actually use the whiteboard to explain some stuff. What I'm going to explain is how we accelerate the vehicles in Chicago Chase. Now, we have three types of vehicle, really: the obstacles, the criminal, and the player. And we want all of them to accelerate differently. We'd like it to be challenging for the player to catch up with the criminal, but he does have to be able to catch up with him. And for the obstacles, well, we don't want them to be as fast as either, so that they are actually obstacles. Now, the way we move things in games usually, and this isn't actually what I do something called, or that I call, integrating ways in the physics engine, is that we take the old position and we add the velocity scaled by a time step. And this gives us a new position. Now, acceleration is about changing velocity, so we also need to update this, and we can do exactly the same thing. And in fact, this process is called integrating numerically by Euler steps, or Euler integration. It's a valid first order approximation in the case where these values vary. So acceleration can vary here as well. You get some errors for their second order. Now, how do we actually want to work with this thing? So I took my inspiration from an old SNES game I played when I was a kid called F-Zero. And other than the massive cars, the way they would distinguish, you had 4 different cars to choose from, was by an acceleration that. So you had one that looked a bit like this, called the Golden Fox. And at the other end of the spectrum, you had one that looks more like this, and this guy was called Fire Stingray. Now, they both have top speeds, and I'll label those Bmax, and these axes B, even though I could use S for speed, because I'm not used to displacement here. That's some kind of civilization scale buck up that we just have to live with. And they actually have different times to reaching their top speeds, which I call these Tmax. The idea is that these cars then have quite different properties. Now, it turns out this one's more massive and this one's really light, but we're not going to use mass in our game. We don't really care about knocking the other car around, except for patch the criminal. So the difference here really is that this guy can recover from mistakes much faster, but his Bmax, if I remember correctly, is something like 450 kilometers per hour. I could be wrong about that. I want to say maybe 420. As I'm thinking about it, my memory tells me 480. And this guy was about 500, although my memory tells me it's probably 494 or something like this. So if you don't make any mistakes, well, you don't run off the track, you don't hit the signs too much or other cars, this guy can get up to speed and stay there and will definitely beat this guy who can never get to this speed. But if you make a lot of mistakes, or maybe if the track has a lot of corners where you want to recover speed from, then this guy has an advantage. And so this adds an interesting dynamic. But that's F-Zero. And if you want to play a modern version of this game, I'd recommend looking at F-Zero 99 on the Switch. It looks really bloody fantastic. And if I had a Switch at the moment, I'd probably play it. Okay, so how do we turn this into something useful? I'm just going to a really big version of the graph. So it's C, and some old curve. We've got our Vmax top speed, and the implicit Tmax at the end curve. Nothing very useful. Well, what we're interested in, I think, is how fast we're currently going, because this thing goes across a time length as if we're just holding the accelerator down. It's fine. When we take our foot off or release the button, what we want is for the car to slow down. Although, in this case, I'm just going to imagine it going at a constant speed. So, if you took your finger off here, you'd keep going like this before you then resume your upward climb. Now, I'll talk about slowing the car down in a different video. But now I just want to think about how to turn this curve into something that can be used in code. So what I'm going to do is I'm going to break this down into a load of buckets across time. That might seem like the wrong way to do it at first, but it does make life quite a lot easier. Bringing it out into evenly spaced buckets here would be lovely for lookup. I'll talk about that at the end quickly. We've got these time steps here, which if I have n buckets, there's n buckets. Might as well have 3 on the end as well. Then each of these little steps, because time starts at 0, is going to be Tmax over n is each of these. Now, each of these points, these lines, they correspond to a point where we've entered a velocity. So here we have v1, then it comes 0, v0. It'll become obvious as I go through. This is cut off to avoid by one error nastiness, which is very easy to run into when you're writing program code that deals with sequences and lookup tables. So we've got all these buckets, n plus 1 points for n buckets. And how do we work out the acceleration for each? Well, we can rearrange that equation we had last time, this one. And we know what the time step is because it's Tmax over n. That's our delta t. And we can say, well, the acceleration is equal to the new velocity minus the old velocity divided by time step. So in this case, it's going to be Tmax over n. Let's go like that as divide sign, simplicity. And then I'm just going to replace this with the ith term, and it's going to be, right in the air again, that's a mistake, vi minus 1 over Tmax divided by n. You can see that v1 minus v0 is the amount of velocity change we have here. We divide it by this time step to get the acceleration change. So that would be a1, to use a concrete example, is equal to v1 minus v0 over Tmax divided by n. So, I mean, I knew ahead of time to do this. This is why I've used n buckets starting at 0. Now, we end up with the lookup table from this where if we're less than v1, and we can never be less than 0, none of our cars, none of our vehicles move backwards in our game. If you want to move a vehicle backwards, I suggest using another acceleration step, because trying to extend this backwards, well, now you're going backwards before the beginning of time. The whole thing is just confusing. It's much easier to have a set curve for that case. So if we're very less than v1, we want to accelerate a1, which is the average acceleration for this bucket here, like straight line approximation to the section of the curve. If we're not going slow v1, well, if we're going slower than v2, then we use a2, the second acceleration. And it goes up for v3 to a3. And it goes all the way up to Vmax, which happens to be the same as Vn. After Vmax, there's no acceleration. We're at top speed. The acceleration is always 0. So let's then Vn, which equals Vmax. Oh, wow. That drew my line in the wrong place. Vn equals Vmax. And I've just remade that mistake. Screw it. That's N. So this lets us say what acceleration we should use based on our current velocity. And that's pretty much it. It's a really simple trick. I talked about making these evenly spaced enables you to replace the lookup. I won't show you how to make these evenly spaced. That's for another video. But what I will show you is just the reason why, because we have to do all these less thans. This might be like 200 if you want a nice smooth curve. So if you want to find out which one of these you need directly, if these are all evenly spaced, you can just take your current velocity, let's call that V, divided by Vmax, and that gives you a number between 0 and 1, and then you can multiply it by n. And if you take the whole number value of that law, to use that weird mathematical notation, this gives you the index to do lookup here. So you don't have to do less than, and less than, and less than, and less than, and a load of chain conditionals. You can just work it out directly and look it up directly. And that's a nice constant time algorithm. It doesn't get slower as your car gets faster. There's probably a much better way to do it, but this is the core here, is transforming your curve and your thing that's in a space of time and velocity into one that's in a space of velocity and acceleration. Okay, so now I'm done with that. I'm going to enjoy my victory cigarette. If you enjoyed that video, please press the like button and do subscribe to the channel. Maybe even share this with your friends and colleagues. And I'll definitely talk more about this, including the how to use the physics engine as your integrator, because I find that incredibly useful. I'll probably cover how to work out how to make all of those buckets have constant gaps in velocity instead of time as well. And yeah, thanks for listening.